Well, welcome back to the second lecture of this course. So today I'm going to maybe define one of the main objects we discussed last time, which is maybe one of these Hyodo Kato stacks, or maybe what I mentioned last time was these analytic Rham stacks. So I'm going to talk about a joint work with Anschutz, Bosco, Lepras, and Scholze on the Rham stacks on far frontier curves. And maybe let me start this lecture with a very important theorem in p-adic theory. So the theorem, maybe to read it to Tsuji, Faltings, and maybe in modern language to Scholze. Says let x over qp. Well, let me talk about k instead of qp. Proper smooth. Algebraic variety. And k, some fun extension of qp. Then one has et al. The Rham comparison theorem of cohomologies. QP equivariant. Isomorphism. Between the et al. Cohomology of K, and maybe the et al. Cohomology algebraic closure of QP, and the Rham cohomology of K, but over K. But of course, these two things live in that they have different bases. This one is over QP, that one is over K. And well, you will be tempted to just base change this to K and get the isomorphism, but that's not true. So actually having this isomorphism p-adic theory is much more subtle, and you need to put a very funny ring here, which is one of these Fontaine rings. One of Fontaine's rings, which in this case is rather concrete, is some discrete valuation field. Discrete valuation field, and the residue field is precisely just a completion of the algebraic closure of KP. So that's say maybe part of one of Fontaine's conjectures that was then proven by different people, different aspects. Maybe the most general one is due to Scholze, that you only need to work with proper smooth rigid varieties and not just those coming from algebraic geometry. But okay, sorry, yes, thank you. Thanks. And let me maybe say a remark that you get from this theorem. Is that the left-hand side, or the way you compute the left-hand side, is computed using essentially some kind of continuous cohomologies. So, well, like maybe in modern language, the way you compute this is you kind of cover this by affinoids that have some charts. You got some kind of perfectoid charts by taking roots of variables, like enough roots. There, these shapes becomes quite acyclic, at least when you compare with some other period shapes like these ones. And then you try to descend back these global sections, and this descending back these global sections just amounts to do some kind of group cohomology. So this is essentially the way you compute these cohomology groups here. On the other hand, the right-hand side is, well, actually computed using genuine differential operators. Well, it's more constructed. So this theorem is maybe contrary to what happens in the complex situation. If you replace this with Betti cohomology, this becomes almost a tautology. Well, meaning that it's a quite simple theorem just coming from some kind of Poincare lemma of integrating functions locally, which is quite simple, at least nowadays. This theorem actually is very deep. It's comparing two very different kind of, let's say, cohomologies. One associated to continuous group cohomology, the other one associated to somehow differential operators. We could imagine Lie algebra cohomologies and so on. So part of this project with Anschutz, Levras, and Scholze on the analytic prismatization, and maybe as well motivated from Pan's work, of course, let's say, part of goal. Analytic prismatization is to somehow modify this left-hand side that is computed, as I say, using group cohomology and perfect order spaces with some other objects that are still close enough to them, but that actually knows about differential operators. Is to somehow enlarge the theory of spaces or far-Fontaine curves, so that let's say this comparison theorem let's say comes from actually studying differential operators on perfect order spaces. Or arises from. So this, of course, sounds very strange because it's well known that in perfect order spaces they don't have cotangent complexes, cotangent bundles. Basically, once you start to extracting roots of a variable, the differentials just get very divisible by p, and when you compute complete objects, then this just get killed. So is not obvious, and in first approach is just completely wrong to even say this sentence, differential operators on perfect spaces. But today, I'm going to convince you that actually this sentence makes perfect sense. We'll study. Right. So, to motivate the construction that will come later, it's very instructive to explain the following construction due to Simpson. Of course, those that know the theory, this would be already something you know. I hope it's helpful for people that maybe are not experts on this. So, let us recall construction of Simpson's the Rham stack. So let me just take again K. Any field doesn't need to be that of characteristic 0. And X, some algebraic variety over K. Let's say smooth, but maybe let me just write algebraic variety. Then a way to talk about linear differential operators on X is by the category of D modules on X, so differential operators linear. X, it needs some kind of categorical upgrade. It's the theory of dx modules, where the x and you can define it as, if you want, the endomorphism, some subsheaf of the endomorphism sheaf of OX, which are K-linears. And these are certain endomorphisms that we call the algebraic differential operators. So essentially just endomorphisms that are given by multiplying by functions and taking derivations and taking compositions of these operations. And now it's unfortunate because I cannot move this up, so we'll need to block this board. I'm sorry about that. Yeah. And maybe, yeah, sorry about that. Just 1 second too. Right. So just like what we had before, we have this category of dx modules. X. And let's say that one nice feature of this category is that, well, you have the structural sheaf is naturally a X module. In other words, you can always just take derivatives of along tangent vectors on OX. That's precisely the structure of OX module. And if you just compute what the write in this way endomorphisms of OX is a D module, this is nothing but the Rham cohomology of X. So in one sense, it categorifies differential operators, and in the other sense, it also categorifies or categorifies the Rham cohomology, the full category of modules that in some sense give you the Rham complexes and the Rham cohomology. Right. So, well, these category modules have been studied several people, have 6 operations. You have these holonomic irregular D modules, Riemann Hilbert, and so on. Let me be focused not in all of these important aspects of the theory, but just in something more concrete that was observed by Simpson. So Simpson said that instead of looking at this category of OX modules, I could just construct a different space. That we call X the Rham. Of course, well, I'm going to be in 1 second what space means, but such that if you take, well, this space ought to have some kind of structural sheaf. And if you take the cohomology of this space of the structural sheaf, you should actually just get the Rham cohomology. So this space, that from now on I'm going to just to call a stack, is nothing but this Simpson's the Rham stack. So there are different ways to make sense of this. Let me give the actual definition and then tell you how this looks like. So let be the category of K algebras. Then we can define this space as, let's say, at least as a functor on algebras that you should imagine as some kind of Joneda way to think about schemes or other geometric spaces. This as before. Then X the Rham is a functor from K algebras, principal to sets, that sends K algebra A to the points of X evaluated in the reduction of A, where this thing is nothing but A modulo the numerical. When this was power go to 0. Right. So you get this definition. Maybe you should think of this more geometrically as an étale sheaf. So this one is an étale sheaf. And whenever you have étale sheaves, or even just étale stacks in the étale topology of algebras, you can construct a suitable category of quasi-coherent sheaves. So given F from these two, let's say, sets, you have a category, let's say a Billian category, of quasi-coherent shifts. So, well, essentially, well, let me maybe not explain exactly how you do this. This is some kind of rule that for any algebra living over this functor and any algebra point, you're given a module, and for any triangle involving these things, then you get an isomorphism between pullbacks of these modules, and these things just have some kind of additional compatibility conditions. So, that. And then you get the following theorem, that will make this in sum, which tells you that if you take an algebraic variety as before and you take it's the Rham stack, then this category of quasi-coherent shifts is the Rham is actually the category of the X modules. Okay. So let me give an example, which is going to be the prototypical example in this lecture for things that will come later, are going to be just kind of different versions of exactly this example here. So let me take X to be just the additive group, just the ring GA. Then if I think of what X the Rham does to A, you just send it to A reduce, which is precisely A modulo the nil radical. But then this means that actually this X the Rham, or GA the Rham, I can write it out as a quotient of GA. This is just A by whatever represents the nil radical. And well, the object that represents the nil radical is we call by definition the formal completion of GA at 0. So, so there is kind of well-known result in algebraic geometry that involves this kind of playing around with the stacks, which is something we call a Cartier duality. Between GA hat and GA. So in maybe modest way to say this is that GA is just the spectrum of a polynomial algebra. So it's of course an algebra, but also this has a group structure that gives rise a Hopf algebra structure on this guy. Additive structure. And well, this Cartier duality at the level of algebras is essentially whenever you have a Hopf algebra, you can take the duals, and this co-algebra structure gives rise an algebra structure on the dual. And then it turns out that if you take the dual of this, let's say as some algebra, this is nothing but the power series on a variable x, where x, secretly I'm thinking of it as the derivative of t, and then you evaluate at 0. It's supposed to be a linear map from the polynomial to k. You're saying that this one is the one that makes this job. And the coalgebra structure here actually gets reflected into the algebra structure. And let me recall here that I assume that the characteristic of k is equal to 0, otherwise that's false. So in this sense, you can think of GA and GA hat to be Cartier duals. Just exchange algebra and coalgebra structure. Well, this one is not itself a coalgebra because the tensor product is not complete, but if you take complete tensor products, you will see that the coalgebra structure corresponds precisely to the algebra structure of GA. So this kind of computations at the level of algebras, they get reflected in the category of modules. So you can look at quasi-coherent shifts on the classifying stack of GA hat, where now I do need to take this quotient, not taking values in sets, but in groupoids, in order for it to not be just a point. This is just the same as this. So therefore, if I take M, some shift in this GA mod GA hat, I do have at least two operators acting on M, one coming from this GA, which is just the underlying coordinate of the ring, and some other operator, this GA hat, that under this Cartier duality arises by somehow taking some sort of derivation. You think what this means. So this has two operators. And call them T and U. And they actually satisfy after basically coming from this action here, that if you do the bracket of this, you can just say 1. And this one comes from GA, this one comes from point over GA hat. Then using this and maybe a couple of other computations, you can essentially arrive to the description that shifts on this guy is just modules for an associative algebra in two variables, where the two variables satisfy this condition. And well, this is nothing but the Veil algebra, which in this case is nothing but the algebra of differential operators of GA. So in terms of coordinates, this is how you can appreciate this kind of relation with differential operators or D modules before. So in general, for X smooth, you can write down the Rham stack as the quotient of X by an appropriate equivalence relation, which if you look at what this equivalence relation is, you can imagine that this is just giving identifying 2 points as long as they are infinitesimally close. So just the equivalence relation given by the formal completion of the diagonal map. So this is pretty close to the way that Grothendieck talk about vector bundles with flat connection as some kind of descent along a second thickening of the diagonal map, for instance. This kind of encode everything there. Right. So there is a huge advantage on thinking of these modules in D modules in this way. So there's a huge advantage. Maybe one of them is that X the Rham is a genuine geometric object. You can actually do algebraic geometry with it. I mean, we kind of did it here just by writing this as a quotient of two geometric objects and trying to understand shifts by the way a group acts in a scheme. you can make more elaborate versions of these ones and obtain, again, like study these more elaborate versions of this using actual algebraic geometry. And the second one is that once you construct this Rham stack in this way, you have immediate access to a six-functor formalism from algebraic geometry. Well, you need to prove a couple of things, of course, but essentially you only need to prove properties and not construct anything. Maybe we'll say quasi-coherent, for instance. So just maybe a remark on this. This six-functor formalism is maybe not, let's say, as prototypical or common as it is maybe the Tal one. It's a little bit strange in the first sight, meaning like everything becomes sort of proper and nothing is almost never Tal. So open immersions are not open immersions but closed immersions in this job role. But this is just the way quasi-coherence behave. We cannot do anything against that. And the world use of this is to pass to, let's say, solid mathematics and so on and do something differently. But this is just how this theory works. And this gives you a reasonable theory of D modules that behaves a little bit different from maybe what a type homology is, and then you can modify your functors and actually get something that looks more like usual six functors in a Tal homology, but this goes in a further construction beyond this. But this is good enough, at least very, very good enough, for example, in order to understand this Bellingson-Bernstein localization, which is something that we're going to discuss later, I hope, at least in the last talk. So UD, basically it's important to have access to this kind of six functor formalism. Right, so let me do this. So we just saw how we can think of differential equations and the rank homology in a purely geometric way using this Simpson's Rham stack. And well, you could think that if we want to do something like this in p-adic geometry, we could try to consider some version of the Rham stack or some versions of D modules there, and then try to see in which sense we can extend this to perfectoids in a reasonable sense. And this is precisely this theory of analytic the Rham stacks I'm going to discuss today. So can do something similar. P-adic geometry, analytic P-adic geometry. And just as a side that is not going to be relevant for this course, we can also do the same in the complex or even in just a mixed characteristic or kind of independent characteristic situation in an appropriate sense. I'm just going to focus on this one. Geometry. This is the theory. Of the So even though the name is not original, just put analytic to the thing that actually exists, the way it is constructed actually requires some effort and a lot of technology that we did not have access until, let's say, 5-7 years ago. Yeah, maybe like 7 years ago. I think it's more. So of course this, so we must work with algebra and analysis simultaneously. That's what analytic means, essentially. So we need a framework to reconcile these two subjects that classically maybe are a little bit tricky to work with. And well, nowadays we do have a very clean answer, a clear answer of what we can do, and that works. We just work in condensed mathematics. I mean, there could be different ways to go about doing this, like Born-logical spaces and so on, but I just find condensed mathematics more clear to me. Let me be a little more precise, because we are actually just care about p-adic things. So in particular, our analysis is non-Archimedean. We can even just focus in something more complete and actually just work with solid abelian curves. And let's say solid tensor products. Right. So maybe let me just highlight one important property of this is that well, p-adic fields are here. Anything that is p-adic is just here. Anything which is adic for some ideal is in here, adically complete. And these tensor products preserve, let's say, tensors of adically complete objects. So in particular, tensors of Banach spaces is just the usual tensor product of Banach spaces that you imagine it is in p-adic geometry, p-adic analysis. So it's just doing the computations that you already will do in a more classical language, but accommodate in an actual abelian category and even better in an actual Dirac category, with all the good properties that you will expect to have from homological algebra. So that's good. We already have a complete tensor, but this is maybe too many algebras to work with all solid algebras, even solid QP algebras. And we want to still have a balance. So let's say we want a framework that resembles let's say rigid analytic geometry. So for example, we do not want to have something like QPT, a polynomial algebra, but instead we would like to have just an analytic affine line, which is ought to be some kind of unit of disks. And similarly, we would not like to have something like a power series ring of T and then you invert P, but instead we would like to have this as just the open unit disk. Right, so even though these ones are perfectly well-defined solid algebras and they are really important, really useful, and we can work with them afterwards in order to make a framework that just resembles perfectos and rigid spaces and this kind of analytic geometry-like flavor, we certainly want that whatever ring evaluated in this guy, like the object represented by this in that category of rings just behaves like this, and similarly the object represented by this in that category of rings just behaves as this one, kind of, let's say, a standard expectation for this. So for instance, we know that these two spaces behave like this, analytic affine line and this open disk, at least when we restrict to Banach algebras. So this is the case. to Banach algebras. So if you take a Banach algebra and you evaluate it in this polynomial, this just gives you the underlying algebra, and well, this is the same as the points of this analytic affine line, like kind of definition. And similarly, if you evaluate a Banach algebra in this algebra, then this just gives you an element that is topologically nilpotent, and that's also kind of the definition of this open unit disk. So Banach algebras, they are very reasonable objects to do analysis. In particular, they do have a nice spectral theory. So Banach algebras. Also have so let me be precise what I mean by this. So let A be a Banach QP algebra. We can define what is called the Berkovich spectrum of A. Is the set of multiplicative seminorms from A to the real numbers that I'm going to just normalize in such a way that the absolute value of P is P minus 1. Again, this is just to normalize this, otherwise you just define some kind of equivalence class of multiplicative seminorms up to kind of exponentiation. So this is just some kind of analog constructions of the same definition for complex Banach algebras, commutative Banach algebras, in which case this set agrees just with morphisms toward the complex numbers themselves. So kind of generalization of this Gelfand transform on Gelfand space. So we can use this, well, whenever we have one of these seminorms, we can complete the ring with respect to that seminorm. I think I never put an end to the, we can note it. So given a point in the Berkovich spectrum that corresponds to one of these seminorms, we can complete A at this norm, and we get a Banach field. K of x, and though with a multiplicative norm. So we do have a map like this. And well, this map almost generally is dense in here, but more precisely, the field generate by the image is dense by well, basically just being the completion of something. So another equivalent way to let's say norm such that again this is pi minus 1. Another equivalent way to define this Berkovich spectrum is just by taking all equivalent, like isomorphism classes of maps from A to multiplicative Banach fields, which maybe you have normalized the norm that this happens, and then or maybe you don't need to normalize this, just maps to multiplicative to Banach fields, where the equivalence relation is basically as long as you have some kind of isomorphism between the Banach fields. Maybe you want that this map shows. The image is essentially dense in this sense. So in other words, like this Berkovic spectrum is just all maps from the ring to fields. So after you have normalized the norms such that this happens, you can make a Banach product of these guys and have a map from this guy to all this Banach. So you should think of this map as kind of just taking a function in your space and just evaluating at all points of the underlying space. So this map is not injective. The kernel is what we call the spectral radical of A. We call it I. So it's essentially all those functions whose values at points vanish. So you cannot detect a kind of norm of this just by evaluating the points. And the quotient, so this kernel is of course closed. The quotient A mod I is what we agree with the uniform completion of A. So an equivalent way to say all of this is that whenever you have a Banach algebra, and let's say you are given with a submultiplicative norm in the Banach algebra, you can, from this submultiplicative norm, construct what is called the spectral seminorm that just consists of taking the norm of powers of the elements and taking roots. This seminorm is not a norm, so it may have elements that are killed. It is at least power multiplicative, so you can take powers out. And the kernel of this seminorm is precisely the same as this. So the completion of the algebra A with respect to this spectral norm is what we usually call the uniform completion, and well, that's just an equivalent way to state what it is. You could think of this multiplicative seminorm, or the spectral seminorm, the one that comes from this Banach product. Each of these fields are given with a multiplicative norm by construction. This Banach product will be given with a suitable suitable norm, which is going to be power multiplicative, because well, you can just test this in each field. It's going to be the sup of all the norms in these fields. And then the induced norm in here, semi-norm in here, is precisely what we call the spectral norm, semi-norm. Sorry? What is sup? The sup? Yes, that's something that in principle require, okay, yeah. I mean, like, the way this Banach product is defined is by taking kind of sequences of objects that are kind of uniformly bounded and such that you can take this sup, no? I mean, like, this Banach product is with respect to the sup, no? And maybe the question is, whenever you have a function here, why this sup is well defined, or but. I mean, if you have a norm in A, then any element up to a power of p is going to be in the elements which are power bounded, and then the power bounded elements also have norm less than equal to 1. Okay, so that was a quick class in functional analysis in p-adic geometry. And we want to have, let's say, just for the sake of working with something that just looks like Banach algebras, that we have all these nice features. We can talk about Berkovich spaces, we can talk about fields, we can talk about, I don't know, uniform completions, spectral radicals, and so on. We want something similar in our rings that are going to model our analytic geometry. Again, something that is still general enough for doing what we want to do, with having an extension of the theory spaces, but maybe not so general such that these rings will show up. So our balance between these two, let's say, desiderata are a class of rings which we call by just function analysis reasons Gelfand rings. So informally, Gelfand rings or Gelfand QP algebras are colimits of Banach QP algebras. By colimits, I just not mean filter colimits, I mean any colimits, so for example, quotients are allowed in solid QP algebras. And I must emphasize that I'm not taking completed colimits as maybe we usually do in the theory of perfect ordered spaces. I'm just taking colimits as they are. So, for example, in my theory of Gelfand algebras, I will have spaces such that over convergent functions with some radius r, which I can think of this as just power series. Such that overconverge in a radius strictly bigger than r. Is again not a Banach algebra itself. It's one of these algebras considered in the theory of Croce-Clone of overconvergent spaces, overconvergent radius geometry. And it is a colimit of Banach algebras of disks of radius strictly bigger than r. Other important space, well, if in the special case when r is equal to 0, this space is just the germs at 0 of GA, right? Just kind of germs of functions. You take colimits of balls going to 0, and you just get this algebra. Another example that is important for this course is these spaces of local analytic functions, when G is a compact p-adic group. So these spaces are not Banach algebras, they are colimit of Banach algebras of just rigid neighborhoods of this p-adic group inside some kind of rigid group. Just neighborhoods that converge to the QP to the points of this p-adic group here. So we certainly do want to consider all of these in the same package. They should have some kind of a reasonable theory, meaning that all of these you can make sense of uniform completion. This one should be Q. This one should be the Banach algebra, the state algebra of radius r, and this one should be just a space of continuous functions. You already have guesses of what should be the uniform completion, and these are Banach algebras that should carry just the same spectral theory we had before. So something you can generally do is just take all these colimits, and this gives you some kind of nice category that you have all colimits. And maybe something that is not so clear is why, when you start to take in all these colimits, all these previous features that you wanted to preserve there actually still make sense for these objects. So in order to see that, we may need to give a different definition of these Gelfand QP algebras, which is the official definition, where by design, there are going to be objects that kind of satisfy all of the previous, that have all the previous features that Banach algebras do. So I'm going to do this, probably end with this definition, and we do a small pause. Let me just end with this definition. So I'm going to write it down, just say 1 second what it means by these things. Let may be a solid QP algebra. Then, well, before this definition of Gelfand, there is a definition of something that is a bounded algebra. It's a bounded QP algebra. If for all profinite set S and map from S to A, well, imagine that S is just a point. Then you would like to say that something is kind of bounded as long as the functions, which is just kind of a map from a polynomial algebra to this, will factor through some kind of space which actually has bounded functions. And the models that we have for these ones are just spaces of functions on disks. So we have exactly the same idea, except that, well, we need to do a version of this where the variables are not just points, the variables are profinite sets. And we just have some notation for these ones. Let me not explain what it is. Just saying that if S is a point, then this algebra is precisely the Tate algebra or the overconvergent algebra we had before. So in some sense, it's just telling you that any function is kind of uniformly power bounded in an appropriate sense. So we can define R in 0 infinity this subspace of kind of functions of radius less than or equal to R, which are basically just those S maps to this one, which is a subspace of this, if and only if this map extends precisely to one of these disk algebras radius R. And in the case when R is equal to 0, so this one actually becomes these germs of functions at 0, we put a special name and we call this the Nagel-Daguerre radical. So you should think of these spaces as kind of having some kind of notion of norm, such that the functions of norm less than or equal to R is precisely this, and the objects of norm 0 is precisely this. So in particular, your norm is not complete, so you should think of this as a semi-norm. And more precisely, you should think of this as a kind of spectral semi-norm instead. And this one should be the objects that have spectral norm 0. So once you have a ring with this kind of characteristics, you can do the same that we have with Banach algebras. You can take the quotient by the object of a spectral norm 0. Maybe we call this just a name. This is called the dagger nil radical. This is a dagger, this kind of notation used for overconverging spaces. We can define what we call this dagger reduction that should be analog to the reduction of a classical ring, just killing the elements of norm 0. And we do have a further construction that resembles more with what happens for Banach algebras, which is this uniform completion. In this case, an equivalent way to do this is just take the elements of which are power bounded, just take the P completion and just invert P. Then there are properties saying that if you take this operation twice, it's just the same as doing it once. So this is kind of uniformly complete. So finally, we say that a bounded ring A is what is called Gelfand. If this thing is a Banach algebra, so in some sense, the only thing we did is some kind of enlarge our ring A such that once we pass to kind of suitable notion of completion, we just get a classical Banach algebra. We just promote the Banach algebras by allowing some kind of decompletions of Banach algebras where we still have a control in the spectral theory. And for such a ring, we define the Berkovich space of A to be just the Berkovich space of U. So just as last comment before the pause. So the previous definition, the one that was written in this board, it says that, well, Gelfand rings are co-limits of Banach algebras. This is almost true. So maybe the thing that is actually true is that bounded rings are co-limits of some generalized version of Banach algebras. Basically, this description tells you that all these bounded rings are co-limits of these gadgets, and these gadgets are just co-limits of special generic fibers of P-complete solid rings. Just take all P-complete solid ring, take just 1 over P, and take co-limits along all of them. And this is precisely the category of these bounded things. So you did exactly this construction, but maybe in a more compatible way with condensed mathematics. Then among all these co-limit of these generalized Banach algebras, well, you first kind of do some first constructions regarding the spectral theory of these ones. So in particular, you define this reduction and uniform completion. And then since you don't want to go too far from Banach algebras themselves, in particular for having a reasonable spectral theory, you just declare something to be a Gelfand ring if the completion of this bounded ring is just a Banach algebra. So as I say, these are examples of these ones. So this one, if you complete, you just get a Tate algebra in one variable. This one, just get QP. This one, you get continuous functions. All of them are just Banach QP algebras. So these ones are examples that land in this category of Gelfand rings. All this discussion here tells you that it has, at least in a formal sense, spectral theory as good as Banach algebras. But okay, I think we can do a small pause of maybe 10 minutes, and then we continue at 11:15. Right, so this is now the point where, well, we did have this category of Gelfand rings, for which let me just not be original and just write Gelfand ring over QP. And now this is, well, certainly we do have these objects that are going to be our basic class of functions for our theory of rigid geometry, where we want to develop and define this de Rham stack. But still there is a step from passing from rings to more geometric objects. This step requires a certain amount of technical but still important steps. So maybe the first one that is easy is just to pass to opposite categories. Just pass to opposite categories. And this produces something that is more like, let me call it Gelfand stacks, which are affinite. So you may wonder why I put stacks if there is not groupoids or floatings around. I don't know. The reason is that any kind of framework where you do algebraic geometry, you can immediately just define a notion of stacks there, and any example of a scheme of algebraic space or whatever is just an example of a stack. So we just jump directly to the more general definition anyway. Also because the theory, in the way, to make the theory run, you just need to consider this general framework anyway. So okay, this one is just passing to an opposite category. Again, well, given our Gelfand ring, we just denote the object in the opposite category by G spec of A. And in contrary to what happens in algebraic geometry, this is not a topological space that is the statistic spectrum. This is more like the sheaf represented by the ring itself. So it's more like thinking of schemes in a Joneda point of view. That's what we're doing here. And now the jump of faith one has to do is just say the magic words and, of course, rely on heavy theory and say that you just pass to analytic stacks and you're done. So I'm just going to comment in this. So you can define, so these Gelfand stacks, they have something that is called a strict topology. So you should think of this as some kind of just general enough topology that allows you to glue as many things as you can glue. And maybe the important feature that this satisfies is that the category of quasi-coherent shapes. And here is also where another important jump we need to do. Maybe in all the previous discussion, we never make or highlight anything about derived structures. Everything was sort of just classical enough. And actually, for this discussion on Gelfand rings, you only care about the classical situation. It is completely insensitive to any kind of derived structure you put on your rings. You only care about the underlying ring. But for this jump to stacks, you actually do care about that. So this topology is such that this infinity category of quasi-coherent shapes, which are complete modules. Let me just say what it is. Complete modules in the derived category of solid QP vector spaces satisfies this end in a very strong sense. So you can define this strict topology for those that know the terminology that is used in this theory. Basically, a map is a strict cover if it is descendable. In the style of Akil-Mathieu. And then, well, you do something a little bit more, but let me just ignore that and just imagine that you're working with shapes. So whenever you have a grotesque topology in the category, well, you get a side. From a side, you can pass to shifts. And very often, you just take shifts on sets in the classical world. Maybe you go to shifts on groupoids if you want to study other objects, because, again, we need to do all of this in higher language. We just go all the way up and take shifts in anima. So again, you should just take this as some kind of black box of what has to be done in order for the theory to work. But once you are there, then you're maybe better because at least you have some kind of nice category, which is even an infinity topos. So in particular, you can just take truncated objects and so on and just deal it as if it was a topos, more usual sense, and then you can start doing geometry with this category. So for sake of clarity of how these objects look like, let me give this just got broken. Let me give 2 key examples of stacks that we're really interested in the rest of the course. And hopefully, these 2 key examples give you a way to think about, again, the main objects that we're going to deal with. So one of the first constructions is this called Betty stacks. So these are supposed to be some kind of realization of topological spaces in analytic geometry. Or maybe more than topological spaces, actually is condensed sets, condensed anima. So the basic construction always goes from profane sets. So whenever you have a profane set, well, you can write this profane set as a limit of finite sets. And then you can define some stack that is maybe denoted as Betty, but that in this course we also can denote it as a smooth. And it is actually one of these ones. It's just the spectrum of a ring. So think of this as just a ring. And it's just the spectrum of the space of locally constant functions of S in QP, which is the same as the colimit of the functions of finite quotients. So it's just a colimit of Banach algebras, so therefore it's one of these Gelfand rings, and then we can take the spectrum of this guy. So just lose the chalk. You have these profane sets, these Gelfand stacks. You have this so-called Betty realization. And then, because of the topology you put in here, any cover profane set and its surjective map is going to be one of these Schritt covers. It's going to be a surjection in this topology. So in particular, this functor just will naturally extend to, for example, condensed sets, which are just sheaves in profane sets. Okay, maybe I would like to say condensed anima to work this, but let me just keep it here. So this is a very nice category. Again, something that gives you some kind of Betty stacks. And examples of condensed sets are just locally compact Hausdorff spaces. And we have the following proposition. So let X be a locally compact Hausdorff space. There could be some kind of light assumptions. Let me ignore this. Then this category of X Betty, to the right category of X Betty, this quasi-coherent shifts on X Betty, is just the same as this kind of left completion of the abelian category of just shifts on the underlying topological space values in solid QP vector spaces. So still, even though you use some kind of, let's say, technical machinery to make sense of Gelfand stacks and even to realize these shifts, at least when you construct reasonably enough, like reasonable classical objects, you still get categories which are just reasonably classical. Here, the only non-classical part is the fact that shapes are taking QP vector spaces, but otherwise is just the same as shapes on the topological space. And again, maybe there is this left completion and so on, but if you're with a finite dimensional locally compact Hyodo space, then this thing just disappears and you don't care about. So a second source of examples is what we call Berkovich spaces. Yes. So this is some kind of generalization of Regis maybe partially proper Regis spaces of these overconvergent spaces of Jose clone. And you can think of this as the following data. So Berkovich space over QP is a map of Gelfand stacks. Yeah. And maybe let me just keep it in post 1 second because I did not tell you something about that, which is actually quite important. Sorry about that. Sorry, I did forget about saying this. So now, well, something that maybe is not so clear from this is what the description of functor of points of this X petty is. This is going to be important for this example. And it turns out that, let's say that X is finite dimensional. Then kind of X petty evaluated in a Gelfand ring is what you will imagine it is. You have a topological space, you have a Gelfand ring, and this one you can construct topological spaces. So this should be just continuous maps from this Berkovich space to the underlying topological space. So again, at the level of functor of points, it's not so crazy. It's just what you will imagine you do when you want to put a topological space into some kind of theory of rings. You just take an underlying topological space of your ring and you just map it to your topological space. And well, this is important, but again, I'm not going to talk about this. Gelfand stacks X mapping 2, or maybe it's a pair. Well, let me just call it this, and maybe put here an adjective and full separated. Where this X is a locally compact Hyodo space. F is, of course, a Gelfand stack, and this satisfies that you can find a suitable cover, something we call strict close cover, set I of this. So strict means that it's refined by some open cover. Such that the base change is actually affinoid, so this is just a ring. And now I told you that you have a map from this one to a Bethe stack. So by this, up to this kind of finite-dimensional thing, this produces for you a map from topological spaces. I mean, you always have a map in this direction, and this map is anisomorphic in these conditions. But you just want that the map from this spec, sorry, from this guy to set E is an isomorphism. So informally, if you just denote X to be the push of the structural sheaf of this one as a quasi-coherent sheaf in this Bethe stack, this one in these lectures are going to denote the underlying unit of this category, which is nothing but the structural sheaf in some sense. We think of a Berkovich space as a pair which is just a topological space and some kind of a structural sheaf, with the caveat that this structural sheaf is maybe valued in these Gelfand rings. So this at least makes this some kind of locally ring space. And this, so a ring space, and then this local condition that we maybe usually use for developing the theory of schemes is just telling you that locally there is some cover such that the Berkovich spectrum of these rings coincides with the topological space, which is the condition put here. So as you see, it's not so far from maybe what we already have done classically for years and years. It's just that in order to make sense of all these constructions, you kind of needed to work in a derived level, and you needed some kind of complete kind of mix between algebra and analysis. And well, once you can make sense of these general constructions, you can go back and just recover what you actually would like to encode within this theory in some concrete examples.
So it's a sheaf on Gelfand rings, or it's only locally?
I mean, both of them, meaning that if you take the full global sections, this could not be connective. But if you take the truncation, you always produce a sheaf anyway. So what you want is that at least locally the full cohomology is just connective, such that locally it actually takes values in Gelfand rings, but still you can always take just connective part of this and we'll still keep having values in Gelfand rings.
Is there a fully faithfulness in the sense that if you're affine, then maps, I mean, there's a notion of maps in your category of...
Yes, so there is a fully faithful functor from Berkovich spaces into Gelfand stacks. And basically the reason is that any Gelfand stacks will have some kind of underlying topological space that you can construct from those of rings. And of course, the passage to topological spaces is functorial on morphing to Gelfand stacks.
But I'm even asking if I'm affine, are maps between Gelfand stacks induced by maps on the corresponding affine?
Yeah. For affines, the maps on Gelfand are just morphings of rings. Yes. Okay, so where is the, yeah. So now with all of these preliminaries, which are actually going to be useful for the rest of, not just for this lecture, but actually to set up the framework for the next 2 lectures as well. So all of this was worth. Let me go back to the original problem and define the Rham stack. In some sense, once you have the language, then the definitions just go exactly the same as you would imagine they go in the algebraic situation, fortunately. So go back to the Rham stacks. So let me just get first a definition and then improve this definition with some additional discussion. Let me just do it for a rigid variety. And let me just take K. Okay, I mean, no, let me just take QP. Some rigid variety. Again, partially proper. Yeah, and all the following are always going to assume things are partially proper. Then we define it's the Rham stack. It's an analytic Rham stack, which is a Gelfand stack. Is the sheafification and it's important to take this of the functor on Gelfand rings. And again, because I'm working in this level, I need the values in anima now. And now, well, we just copy-paste the formula we have for the algebraic Rham stack. So recall that the formula was we did introduce some notion of reduction, then we just evaluate this guy in the reduction of the ring. And we do exactly the same in here. But now this reduction is played by this dagger nil radical dagger reduction. And then there is some kind of additional simplification that we're going to discuss maybe in some minutes. So let me give examples of this. Sorry? For a strict topology, yes. For the topology that exists in these Gelfand stacks. So some kind of very monstrous topology, but still we just simplify for this. And what matters is that because this topology quasi-coherences were invariant for this topology, then the pre-sheaf and the sheaf, they do carry the same theory of quasi-coherent sheaves. That's maybe the most important thing that we actually care. So at least at the level of quasi-coherent sheaves, this definition and the sheafification does not see the difference. So let me just take the example of X to be the analytic affine line. But I just want to keep denoted GA itself, not GA only. Then, well, X on a ring A is just this dagger reduction after sheafification, or before sheafification, sorry, which is the same as A modulo this nil radical. So these algebras of over-convergent objects define some kind of disks of different radius, some over-convergent disks. And if R is equal to 0, we have this space of germs of functions. On GA, that's something we denote GA dagger. You can think of this as an intersection of disks tending to 0. The intersection is a limit, and the level of algebra limit goes to a co-limit, which is precisely this guy here. Then by definition, the nil radical, the points of the nil radical are precisely the objects co-represented by this ring. So in other words, this GA de Rham, again, even after sheafification, because sheafification commutes with co-limits, is just this quotient here. Just take this A and divide by the thing that represents the nil radical, which is precisely this one. And again, this one is just acting by translations. So this is essentially the same formula we had for the algebraic Rham stack, except that we changed formal completion by some kind of over-convergent neighborhood. Otherwise, it's just the same formula. You may wonder how this relates with D modules. Let me sketch how this works. So was before like this space. Let me just discuss these global sections. This some algebra I may want to denote like this. It's just holomorphic functions on a variable t. On the fine line. Well, computation, you can write it down this way. So certainly you do have an operator in your modules that at least look like these holomorphic functions. But then you also should have some other operator that comes from this group. And then you can also still use some Cartesian duality. So there is a Cartesian duality. Between GA and GA dagger. So that, and maybe now you need to take the right categories. This is just the same as D of Gn. So in particular, we get another operator. That maybe I would like to denote like this. So some other operator that we know from the algebraic situation that is just the derivation along T that also converges as a disk, as a affine space. So then, at least if you have shifts on this GA the Rham, you should be able to produce modules on certain algebra. On QP vector spaces, where this is some algebra of infinite order. P-adic differential operators. Some algebras that has been studied very deeply by Ardakov and Arkhov-Wasley. Indeed, yes.
So, but here you're writing a module.
Yes, but I'm writing the module of the dual of the coalgebra. So the co-module corresponds to functions in this space, but we discussed that if you have a coalgebra, the dual is going to be an algebra, and this corresponds more to the algebra.
I see, but then why is it?
No, you're not saying it's an equivalence. I'm just saying you can forget.
Oh, sorry. Okay, I see.
Yes, like in general, this will embed fully faithful, and you can describe the image. So these D modules are related with these ones, and with some work, you can actually prove that basically it's just a refinement and kind of generalization of T of Arkhov. Let me not do that right now. You're saying that by looking at the same equations and doing similar arguments, which in this case relies on this Cartesian duality, you can obtain similar descriptions of shifts in terms of differential operators as it occurred in algebraic situation. So as long as you have coordinates, you have a good idea of how these things look like. In some sense, the only additional feature that you're doing is just having the usual differential operators, and then you impose some growth conditions on the differentials and maybe the variables of the spaces. That's what this analytic Rham stack is doing.
Does that how to describe the essential image?
Yes, I mean, the essential image, so this algebras is something that is called Frechet-Stein. So there are just limits of Banach algebras. The Banach algebras would be like the Banach versions of these completions. And then the essential image is just the limit of module categories along one of these presentations as Frechet-Stein algebras. Some kind of quasi-coherent in both the t direction and the differential direction. Right. So in general, for a rigid space, you can also think of this X the Rham just as the quotient of x by some sort of equivalence relation, and this equivalence relation is again analog to what happened in the algebraic situation, where instead of looking at some formal completion, you look at some kind of overconvergent neighborhood. So this is some analytic stack with same topological space, a Berkovich space, with same topological space as x, but the functions are now just germs of functions. It doesn't matter that it's smooth for this construction, but let me say it's smooth for. I mean, this is also true if it's not smooth, but let me just say it's smooth for just keeping with the previous example. Right. So this is good. At least we have something that we want at the level of rigid geometry, but recall that the goal was to have a good theory for perfectoids and far-from-ten curves and so on, and we're still far from that. Meaning even this description relied on having specific coordinates that you couldn't say that this is basically the same as having differentials and making set-on differentials. So to understand the Rham stacks more generally, one has to introduce again some kind of basis for the topology of Gelfand rings. Sorry. A certain basis that is going to be deep enough in the topology such that we can actually see a lot of new features that we can not just see with just usual Gelfand rings. So this requires definition of a couple of things. So a Gelfand ring so the first one is something we call nil perfectoid. If, well, the uniform completion agrees with the dagger reduction, and this Banach algebra is a perfectoid. QP algebra. So somehow it's some sort of thickenings of perfectoid spaces, perfectoid rings. Second one is A is totally disconnected. If this Berkovich space is profinite. So usually in the theory of perfectoid spaces, you want to go to a cyclic kind of perfectoid rings, and one first step you do that is by kind of making the underlying topological space as cyclic as possible, which is nothing but being profinite. We also say strictly totally disconnected. If the residue fields are algebraically close. For all x in the Berkovich space. So, well, this one is again some sort of a standard technique in perfectoid geometry, consider some kind of acyclic perfectoid spaces in some sense. This one looks a little bit more mysterious, but let me just say that in analytic geometry, or p-adic analytic geometry, analytic p-adic host theory versus integral p-adic host theory. You have these nil perfected rings. And here, the analog of this is precisely this category of semi-perfected rings. So these are things which are quotients of perfectoids, and I claim that in this p-adic situation, analytic situation, these nil perfectoids just play exactly the same role as these semi-perfectoids do. So just to give an example of this is that if you have something like, let's say, a Banach algebra in some kind of algebraically closed field, then this one usually admits some sort of cover by this, which is one of strict cover. In this situation, it's going to be one cover, basically because you do have a section as a module. And these tensor products, they are not longer perfectoid. So this one is perfectoid, but these tensors are not perfectoid. But still, at least in the language, they're going to be semi-perfectoid. So they're just quotients of perfectoid spaces by some kind of closed ideals. And it turns out that these guys are actually nil perfectoids in this language. So even more generally, if C is semi-perfectoid, over set P, then this thing is automatically going to be a Gelfand ring. And if you take the dagger reduction, this actually just going to agree with perfectoidization of C itself. So this process of passing to the dagger reduction is something that in integral p-adic will correspond to just taking the perfectoidization. Sorry?
This is like André's lemma.
Yes, exactly. Yes, exactly. Yes, this is a non-trivial statement indeed. Yes, that's a consequence of André's lemma, or just the fact that there is some kind of, for any statistic closed subspace of a perfectoid, there is a perfectoid quotient of the ring who has precisely the same spectrum. Indeed, yes, that's a non-trivial statement. Yeah, it's quite important. So, well, I think unfortunately I will not have much time to discuss about these Hyodo Kato things, but at least I want to introduce maybe the most important part of the theorem today. Next time I will continue with this Hyodo Kato and discuss some aspects of the prismatization. Maybe that even makes more sense. Yes. Exactly, that's what I'm going to discuss right now. Yes, indeed. So as Vincent say, we have one nice lemma, is that under mild kind of finite dimensional assumptions, something that we called in the paper quasi-finite dimensional. So essentially any kind of object you actually get in practice is of this shape. And if you do not have an object of this shape, it's because you did some kind of technical construction more than a natural construction. So rigid spaces, prototype things over rigid spaces are basically examples of this, and essentially that's kind of what determines that in some sense. Any Gelfand QP algebra that needs a strict cover by strictly totally disconnected, sorry for the abbreviation, nil-perfected space. Nil-perfected ring. So these strictly totally disconnected nil-perfectors, they do form a basis of our topology. So we do have like an alpha cyclic optics in a strong sense. Then the theorem, the first part of the theorem goes as follows. So let X be a Gelfand stack, or maybe, yeah. Let me. Yes, so I only define this. Let X be a Gelfand stack. Which, again, underlying this, there are some technical finite dimensional assumptions, which I'm going to ignore here. Then the shiftification of X the Rham of the of this thing, some kind of the functor sending A to a dagger with us, is precisely the functor that sends A to is dagger reduce, sorry, uniform competition, and well, basically just because these two things agree on nil-perfecteds, and when restricted, to these strictly totally disconnected nil-perfectoids, well, it's almost not necessary to shiftify. Let me not say that it's almost not necessary. So for instance, if X is a rigid space, it's not necessary at all. So just to finish quickly in these last minutes, this theorem, together with some refinements that go in the paper, they actually produce something much better for you. So actually, you do have an analog in theory of Gelfand stacks and all of this in maybe more modern, but still a little bit more classical p-adic theory, still modern p-adic theory, which is this theory of V stacks of Schulze, diamonds. So we do consider a variant of this theory of V stacks that fits better in our setup, which is when we don't care about the plus, we just care about the Berkovic spaces. This theory is what we call R stacks. Some kind of category of V stacks, let's say over QP.
You still do not care about stuff, right?
Sorry?
Even with Gelfand rings, you still do not care about stuff rings.
We don't care, yes. Yes. So this one cares about the plus ring, this one does not care about the plus ring. And so this is just basically shifts on perfect spaces with respect to the R topology, which is just this topology given by the Berkovic space, just by surjections. And then a refinement of what this theorem means is that there exists an adjunction between arc stacks over QP and Gelfand stacks. Again, there are some mild assumptions, some finite dimensional conditions, where this one is the right adjoint, which I'm just going to call the Rham, and this one is the left adjoint that I'm calling perfectoidization. And this is such that actually both functors preserve colimits. So this basically just means that this Rham stack satisfies arc hyperdescent. Is not formal, yes. That's not formal. This perfectoidization functor is basically just the restriction of x to perfectoids, totally disconnected. So these strictly totally disconnected perfectoids. You have a functor on this, you can just restrict on them, and they actually going to give you an arc stack. So that's a kind of cheap way to construct something here. And x the Rham, so you have a diamond and you apply this the Rham. And you evaluate in A, and A is one of these STD nil perfectoids. And this thing is actually just the y of just the perfectoidization, which is nothing but the uniform completion of A. So this formation of the Rham stack, it does satisfy a law of descent. In particular, you do have some kind of reasonable functor that comes with colimits defined directly on perfectoid spaces that just spreads out to all diamonds on these stacks. And let's say a formal consequence of this is that whatever the rank homology this space is going to give you, which is just global sections, will automatically satisfy arc descent. So unfortunately, due to time, I do not have space to give examples of these ones, which is maybe the title of the talk. But let's do this in 1 weekend. We start with examples of this Rham stack of these Hyodo Kato stacks, and again, other examples of perfectoid and over-convergent spaces. And then we can also use this to motivate the construction of this prismatization. But okay, I'm going to finish now. Thank you.